I probably will not be able to register all of this course, so nevertheless, let's start. Now, what are these frequencies? Okay, so we said that the possible values, the k should have this value, 1 over c square root of omega squared minus omega mn squared, where we define omega mn squared as m pi over b squared plus n pi over a squared. You see, what we, and let me also, the electric field, the z component of the electric field, the general form, will have this expression, a some coefficients, cosine m pi over b, y, x, now y, sine, this is our cosine n pi over a x. And this is the general form, e to power I kz minus omega t. Now, first of all, you see, what are omega m and what do they correspond to? Well, you see, if you look at this expression over there, there is a restriction on the possible values of omega. Omega should be larger than omega mn. Now, if you are sending some wave omega, is basically what you will do is you have your waveguide, you will be sending an electromagnetic wave into this waveguide. And the wave that you send can have an arbitrary frequency omega. And if you look at the expression of omega mn, it will be basically, it will grow with the values of m and n. But eventually, for some values of m and n, this condition will not be satisfied. So you will not be able to create such propagating waves in your waveguide. So basically think of it like this. If you are playing the flute, you can only create certain frequencies, not all of them. This is just like, in a sense, similar to that. You can create certain frequencies in your waveguide, not all of them. Well, basically you have ranges of frequencies that you can create. So that these omega n values are kind of a cutoff frequency. So each of these modes, they have a characteristic cutoff frequency, and you can only create electromagnetic waves which are faster, oscillating faster than that cutoff in that mode. Now, what happens if you send a wave omega that doesn't satisfy this condition? Well, you see, k just becomes imaginary, and it doesn't really propagate in the z direction, it just decays exponentially. Then you can define this skin depth, so it will be able to penetrate only that distance, and beyond that distance, there won't be any wave in that mode. And furthermore, you see, there is a smallest possible value of omega mn. M and n, each one can be 0, but they cannot be both 0 at the same time. So there is a minimum value of omega that also tells you that there is a minimum frequency that you can transfer using your waveguide. If you are sending a wave with a larger frequency, it will not be able to go through.
Şimdi biz bu waveguide'ı kullanarak işte gönderdiğimiz dalgaya yön veriyoruz aslında, değil mi?
We can. That is what we are saying. I mean, in this case, we are not really guiding it because these are straight. The problem we have studied is just a straight waveguide. But in principle, you can just make waveguides that will just go around corners, let's say. In such a case, you will be able to guide your wave. So you see, what is actually happening over here is just like a fiber optic cable. You get internal reflections. And as a result of these internal reflections, if you just bend your waveguide, it will also bend with it. The wave will also go around it.
Peki hocam hiç ortada böyle waveguide yok işte. Atmosferde elektromanyetik dalga gönderiyor. Ama şuradaki kişinin almasını istiyorum. Bunu nasıl yönlendireceğim?
Well, you have the refractive index. You have to be controlling the refractive index. Or you put some mirror over there. You see, the things that we have seen up to this point that can change the direction of an electromagnetic wave is either reflection or entering a different medium, refraction. So those are the only two means with which we can change the direction of an electromagnetic wave. But in general, it's not so easy to create a wave that is propagating in a single direction. You see, even now when I'm speaking to you, I'm creating not an electromagnetic wave, but a sound wave. Anybody behind me will also be able to hear it. Some of it will be due to reflection, but not only that. I mean, the way, even if we were in the open air, people behind me can hear it. The closest we have for a directed electromagnetic wave is a laser. So now let's start our discussion on, well, we are kind of jumping chapters. Now we are going to chapter 12. Electromagnetic potentials. Now, if you remember our discussions on electrostatics and magnetostatics, in electrostatics we could define an electrostatic potential because the curl of the electric field was zero, and so that the electric field we could write as kind of in terms of a gradient of a scalar function. So that was our electrostatic potential, and the magnetic field, its divergence was zero. So we could write the magnetic field as the curl of some vector field. So that was our vector potential. But when we started electrodynamics, we kind of lost this. You see, the divergence of B in electrodynamics is still zero. So this tells me that the B can still be written as the curl of some vector potential. So this is still valid. But the divergence of E, the curl of E is no longer zero. The curl of E is equal to minus del B by del T, which tells me that E is not equal to the minus gradient of some scalar function. So we still have this concept of vector potential in electrodynamics, but we don't have this concept of scalar potential, at least not in this sense. But we can still define some kind of a scalar potential. Let's see how we can do that. Now the curl of E is equal to minus the time derivative of B, which we said that it is the curl of A. But the position derivatives and time derivatives, I can just change their place. This is minus the curl of the time derivative of this vector potential. So the curl of, if I just combine these terms on the same side, curl of E plus the time derivative of this vector potential is zero. Now I have, it's not the electric field, but I have something else that can be written as the curl of, whose curl is zero. But if a vector field has zero curl, it can always be written as the gradient of some function. So this tells me that E plus del A by del T, this is equal to minus the gradient of some function. Or the electric field is minus the gradient of phi minus del A by del T now. You see, in electrostatics, where nothing depends on time, we just recover the ordinary electrostatic potential. This phi just in the static limit becomes our electrostatic potential. So these are our new potentials, E and B. We still have two potentials, well, four, let's say, counting the components, three vector potentials, making this vector potential, and one scalar potential. So we can write all the electric and magnetic fields in terms of these potentials.
Hocam şuradaki manyetik alandaki vektör potansiyelle elektrik alanındaki aynı mı?
Let's look, let's see our derivation. What we did, we have that B over there, which we replaced it in terms of A. So this A is the A describing our B field. So that this is the same A, this A is the A corresponding to our B field. So this A in the expression of the electric field and this A in the expression of the magnetic field, they are the same A. They are not different. Now, our purpose in the next couple of days, let's say, will be to be able to find some equations that these A and phi fields satisfy, so that afterwards we will be able to derive the potentials corresponding to a point charge. And once we have the potentials corresponding to a point charge, whatever charge distribution we have, well, that charge distribution we can write as a sum of point charges. So it will be just the potential they create will be the sum of the potentials created by point charges. So in that case, in that way, we can study an arbitrary charge distribution moving in an arbitrary way. In electrostatics, we just assume that they were at rest, but we won't need to make that assumption anymore, for example. And then we will see what new phenomena arises. So we will see how radiation comes about, etc. So that will be the way we will proceed. First, let's try to find what these A fields and phi fields, what kind of equations they satisfy. Now let's see, we have four Maxwell's equations. One is that the divergence of B should be 0. The other one was the curl of E should be equal to minus del B by del T. So these two equations we had already solved. That is the advantage of defining these potentials. So the moment that we write the electric field in this form and the magnetic field in that form, those two equations are solved. So there are two more equations we need to solve only. Now let's try to see what those two remaining equations imply for the phi and the A field. We will be working in vacuum for this problem. So what do we know? Okay, we already use the fact that curl of E is equal to minus del B by del T. The other equation involving the position derivatives of E was the Gauss law. Divergence of E, this should be equal to rho F, no, not rho over epsilon. Now let me write it in this form. Well, in this form it is valid both in vacuum and also in a linear dielectric. So in vacuum, this epsilon is just epsilon 0. In a linear dielectric, well, that is just epsilon, the permittivity of that dielectric.
When you write rho F, what is rho over epsilon 0?
No, rho F is this rho. This rho is the free charge. In vacuum, that is the only charge. In a dielectric, it's the charge that is not bound to atoms. Well, we know that E has this form, so let's just substitute it. So we get the minus the Laplacian of phi minus del by del T of the divergence of A. This should be equal to rho over epsilon. So this is one equation that we have for phi and A. Again, if we would go to electrostatics, statics where nothing depends on time, so this just gives us the electrostatic Poisson's equation. Now let's look at our other equation. So the other equation that we didn't use was the curl of B is equal to mu times J minus mu epsilon, no, plus mu epsilon del E by del T. This was our other equation that we need to satisfy. Well, B we already know is the curl of A. This should be equal to mu J plus mu epsilon del by del T. E is minus the gradient phi minus del A by del T. Let's try to simplify it a bit. You see the curl of A is the gradient of divergence of A minus the Laplacian of A. And let me write it in this form. Mu epsilon del squared A by del T squared minus the Laplacian of A plus the gradient of the divergence of A plus mu epsilon del phi by del T. This should be equal to mu times J. So what did I do? I took this term, moved it to the other side, so that became the second time derivative of A. So this is the second time derivative of A. I just moved it to the left-hand side, so it's this term. Well, this term is this one over here. And then I have these two terms. The first one is the gradient of the divergence of A. It is this term right over here. And this one is this term. I just took the gradient out. So gradient and time derivatives, they can just change I can change their order. So I just end up inside the gradient mu epsilon del phi by del T is equal to mu J. Mu J is this one over here. Well, they don't look nice, that's for sure, at least in this form. And when we had these Maxwell's equations in terms of the electric and magnetic fields, there was quite a nice symmetry between the equations satisfied by the E field. They look very similar to the equations satisfied by the B field. We kind of lost that symmetry. Let me just try to write these two equations. I mean, you see the equation for phi and the equation for A, they just look completely unrelated to each other. Let me try to write down the above equation in a slightly different form. You see that equation is minus the Laplacian of phi minus del over del T divergence of A is equal to rho over epsilon. Well, let's see. Here I have the divergence of A, here I have the divergence of A. So that combination, let's say, looks nice. Let's try to add that combination over here. Plus mu epsilon del phi by del T. But you cannot just add things to your equations, add things that are not necessarily zero to your equations and hope that the equation still holds. So if I'm adding this term, I have to subtract that term also. So you see this term cancels this term over here. Well, at least in this form, they look more symmetrical. You see here I have mu epsilon times the second time derivative of scalar potential or the vector potential minus the Laplacian of scalar potential or vector potential. Here I have the same combination. In this one I have the gradient of that combination. In this one I have the time derivative of that combination. And on the right hand side I have my charges. I did not. You see, this is what I obtained for the A equation straight away. Here, I just wanted to create the same combination with the divergence of A. But to have that combination with for the divergence of A, I have to add this term, but now I have the second time derivative of phi. I have subtracted the second time derivative of phi, so I have to add it. So you see, it would have been nice if we could somehow guarantee that that term was 0. This parenthesis. You see, if that parenthesis were, for some reason, 0, then the two equations will be identical. Of course, the right-hand side will have some different functional form, but the kind of the differential equation is I have this mu epsilon times the second derivative minus the Laplacian acting on something equal to some other known thing. So that will be our equation, and we will be able to deal with that one nicely. Of course, there is no reason for that to be 0, unfortunately. But let's see. Now, we had these definitions. Now, suppose I change A. Instead of A, I use A plus the gradient of some function lambda. So let's see how the B field changes. Curl of A becomes the curl of A plus the gradient of lambda, which is the curl of A, or this is B, curl of A plus the curl of the gradient of lambda. But curl of a gradient is always 0. What remains is the curl of A. So the curl of A is nothing but our B. So B just stays the same. So to describe the same magnetic field, I can either use A or I can use the A plus the gradient of lambda. They give me the same B field. And since our physically measurable thing is the B field, I don't really care whether I use A or A plus gradient lambda to describe the B field. They give me the same B field. Let's see what happens to the electric field. Which is minus the gradient of phi minus del A by del T. Well, I will assume that I also change phi. I don't know how, but I change phi. This becomes minus the gradient of, let's say, phi prime. I don't know what phi prime is. Minus the time derivative of A plus the gradient of lambda, which becomes minus the gradient of phi prime minus del lambda by del T minus del A by del T. So what I did was, okay, here I have the minus the gradient of phi prime, it is this one over here, but now I have minus the time derivative of gradient of lambda. So it has a minus sign, so this is here, it's a plus. So it's minus the gradient of the time derivative of lambda. This term was already over there. Phi prime, well, I already changed A. Phi prime is my new phi prime. I also changed phi to phi prime. I don't know what phi prime is, but now I see that if I define phi prime to be phi minus derivative of lambda by del T, so this just becomes minus the gradient of phi minus del A by del T, which is nothing but E. So you see what I did? Yeah, let's wait for it.
So changing the scalar potential, how we changing
Along with changing the vector potential, doesn't change the electric field. You see, what I am claiming now is that if instead of A, I use A plus the gradient of lambda, lambda being some arbitrary function, I don't impose any condition on lambda, and at the same time I change phi into phi minus the time derivative of exactly the same function lambda.
So this is your change.
This is my change. This is how I define my change. I change both the scalar potential and the vector potential at the same time. And if I make these changes, the electric field does not change. The magnetic field does not change. You see, I cannot really measure the scalar potential or the vector potential uniquely. Even in electrostatics, what we did was, if nothing depends on time, then we can still shift the potential by a constant. So we couldn't measure that constant, we just defined that constant somehow. Now in electrodynamics, we still cannot measure phi or the vector potential itself. What we measure is the electric field and B field. So as long as the electric and B field is not changed, if I change phi or A, well, so what? The electric and magnetic field stays the same. Those are the measurable things. So what this tells me is that for a given electric and magnetic field, the choice of the vector potential and the scalar potential is not unique. There are in fact infinitely many possible choices of scalar potential and vector potential that will correspond to the same electric and magnetic field. That is the lesson we learn from this consideration. Now, this is what we call the gauge transformations. No, you see, we are not really defining it. The theory already tells me that, you see, when you are defining something, some function, you have to make sure that it is well defined. How do you define it? We said that, okay, we could talk about phi, we could talk about A, such that the B field is given by the curl of A, and the E field will be given by minus the gradient of phi minus del A by del T. But how do we determine these phi's and A's? So that was kind of the question, our first question that we asked. Now this question is even more complicated because there is no unique phi and A that corresponds to a given E and B fields. There are infinitely many of them. So it's not that we wanted this, it just came out of the theory. So when we are looking for solutions of A and phi, we have this arbitrariness. So that tells me that the solutions for phi and A will not be unique. I mean, if I know E, if I know B, the solution of these equations is not unique. There are infinitely many of them. Nevertheless, I can choose one of them if I impose some additional conditions. Now let's see what these transformations do, for example, to divergence of A. So let's say we are given an A field. Somebody just tells us that, oh, you see, I have this E and B field, the corresponding vector potential is A, the scalar potential is phi. Well, the divergence of A, if I make that transformation, will change. It will become the divergence of A plus the Laplacian of lambda. Now this is, although to start with, it comes about as a nuisance in the sense that it doesn't allow me to determine that gauge symmetry. This is called the gauge symmetry. that nothing changes under this transformation. Now that gauge symmetry, although it prevents us to uniquely determine A and phi because they are not unique, there are infinitely many of them, that freedom allows me to change the divergence of A without changing the E and the B field. So I can change the value of divergence of A. For example, if you want, you can set the divergence of A to 0. So you see there are infinitely many vector potentials that corresponds to the same E and the B fields. These vector potentials will have different properties. Some of them, if not just a unique one of them, will have its divergence 0. So we might say that, okay, we have infinitely many vector potentials and scalar potentials, but I'm not looking for any one of them. I'm looking for one of them, which has the divergence of A is equal to 0. We have that freedom now. In a sense, it's just like the choice of the coordinates. You see, if you are studying the projectile in this direction, you don't choose arbitrary coordinates. You just choose one of your directions along the horizontal component of the velocity of the projectile. It simplifies your life. So similarly here, I have infinitely many vector potentials and scalar potentials that correspond to the E and the B field. I don't look for an arbitrary one. I'm looking for one that will simplify my life. The other ones will be related by gauge transformations. Well, why do I want the divergence to be 0? Well, let's remember our equations for our potentials. We obtained two equations for our potentials. One was minus the Laplacian of phi minus the time derivative of divergence of A was equal to rho over epsilon. So for example, if you just say divergence of A is equal to 0, if you would like to impose that condition, then what you obtain is just the Poisson's equation. Remember, this rho is possibly time dependent. So we can choose the divergence of A is equal to 0. This is not something we drive. This is a condition we impose on our potentials. We can impose this condition because we have that property that by choosing a suitable value of lambda, I can make sure that divergence of my vector potential is 0. If he gives me some vector potential, I can find some lambda which will make the new vector potential that I obtain from his one to have 0 divergence. So I can always choose such a vector potential. Well, if this is the case, then my equation for the scalar potential just becomes the Laplacian of phi is equal to minus rho RT over epsilon. And now I know my solution for phi. Phi at the point R at the time t is nothing but integral of rho of R, let's say R prime t divided by R minus R prime 1 over 4 pi epsilon 0 integrated over R prime. How do I know this? Well, this is the equation I had in electrostatics also. This is the equation we studied in electrostatics. Now just keep in mind, this time over here and this time over here is the same. So if you change the rho, let's say at this point, at this instant, the potential in the next galaxy changes exactly at the same instant. No, I don't. You see, I don't yet know what A is. A satisfies a different equation. The equation that A satisfies will still be this one. Mu epsilon del squared by del t squared minus the Laplacian operator acting on A. I think it was plus the gradient of the divergence of A plus mu epsilon, no, plus del phi by del t. This should be equal to J over mu. Now divergence of A is 0. This is 0. I know what phi is. So just divergence of A is, set this to 0. I replace phi with this integral expression over here. You obtain an equation for A, for the vector potential. You have to solve that equation for A subject to the constraint that the divergence of A is equal to 0. So you have to solve this equation plus the divergence of A is equal to 0 equation at the same time to obtain the value of A.
Hocam şimdi şey dediniz ya, işte burada bir potansiyel değişirse başa galaksiydeki de hemen değişir dediniz. Hani ışıktan hızlı information taşınamıyor.
Is this an information? Yes, potential changes, fine. But we are not measuring the potential anyway. We are changing the electric field. We are measuring the magnetic field. As long as the electric and magnetic fields do not change instantaneously, you will not be carrying information. You see, the electric field has two components. One phi and the other one from E. You see, E is equal to minus the gradient of phi minus del A by del T. And it just turns out that this combination does not change instantaneously. Phi changes instantaneously. There is some part of A which will change instantaneously, but those two parts cancel each other. E doesn't change instantaneously. Now this is called gauge fixing. And so basically that transformation we had defined that just given a vector potential and a scalar potential, I can just change it in that way. That's above. And if I change it in that way, the E and the B field does not change. That change is what we call the gauge transformation. That tells us that there are infinitely many vector and scalar potential pairs that correspond to the same E and the B field. Choosing one of them among these infinitely many pairs is what we call the gauge fixing. So this condition, divergence of A is 0, is our gauge fixing condition. So this equation tells me that this solution is unique. So although we started by saying that there are infinitely many vector and scalar potential pairs corresponding to the given E and the B field, by imposing this condition, I reduce that possibility, that infinitely many choices. I just focus on a single one, which has this phi. Among these infinitely many vector and scalar potentials, I picked up one by imposing this condition. That is why we call this gauge fixing condition. If you just change your gauge, if you make that transformation, this condition will no longer be satisfied. This one. Well, that would have been great. Let's see if we can do that. Well, now what is the coefficient over here? Can somebody remind me? Okay, so this gauge fixing condition is what we call the Coulomb gauge. But, well, this Coulomb gauge, we already have seen it in magnetostatics. You see, in magnetostatics, we already assumed that the divergence of A should be equal to 0. We made that choice. But that Coulomb gauge, when you look at the electrostatic potential, it has this kind of weird implication that the potential changes instantaneously everywhere, which seems to contradict at first sight Einstein's special theory of relativity, which says that no information can move faster than the speed of light. Well, there is actually not a problem Because although phi changes instantaneously, if you just calculate the A and put it in the expression for the E field and B field, E and the B fields do not change instantaneously. So there is no problem, but nevertheless, it looks as if there is a problem at first sight. Now, a better condition would be, as your friend pointed out, it would be nice if this combination was equal to 0. So let's see, is it possible to choose a lambda that would satisfy this, make sure that our new vector and scalar potentials make this combination equal to 0? Does such a lambda exist? Now let's first look at that. Now these are my gauge transformations. Let us just start with some A0 and phi. Let's say that Puyan had just found out that this A0 and phi 0 potentials correspond to my E and B fields. But this A0 and B0 don't make that combination 0. Now my question is it possible to find a lambda? So I said A is A0 plus the gradient of lambda, phi is equal to phi 0 plus minus the derivative of lambda with respect to t, such that divergence of A plus mu times epsilon del phi by del t is 0. Is it possible to find such a lambda? If we say that it's always possible to find a lambda such that this will be 0, then to start with, rather than trying to understand where Puyan came up with the initial A0 and phi 0, we might, at the beginning, we start by looking at a and phi that makes this 0. So this might be our alternative gauge condition. Well, if this is 0, let me just put A0 and phi 0, A and phi in terms of A0, phi 0, and lambda. So this tells me that the divergence of A0 plus mu epsilon del phi 0 by del t plus the Laplacian of lambda minus mu epsilon del squared phi del squared lambda by del t squared, this should be equal to 0, or mu epsilon del squared lambda by del t squared minus the Laplacian of lambda. This should be equal to divergence of A0 plus mu epsilon del phi 0 by del t. So the question is, does this equation have a solution? So Puyan just gave me these A0s and phi 0s, so I know what the right-hand side is. This is nothing but a driven wave equation. So here, this is our wave equation. There is an external force driving the wave. But this always has a solution. And our nice mathematician friends, they prove that such equations always have a solution. Now, what this tells me is that if, by some means, somebody gives you any vector and scalar potentials corresponding to a given electric and magnetic field, you can always find a second set of vector and scalar potentials for which this combination is 0. It always exists. So to start with, we can just start looking for that one rather than looking for an arbitrary vector and scalar potential. Now this condition is what we call the Lorentz gauge. So for us, most of the time, you will either see the Coulomb gauge or the Lorentz gauge used. let's see. First of all, we can make such a gauge choice. You see, the gauge choice is ours. It's just like choosing this lambda. You can choose an arbitrary lambda. I just choose a lambda such that my vector and scalar potential satisfies this gauge condition or gauge fixing condition. So we can always find for a given E and B field, we can always find the vector and scalar potentials which satisfy this condition. It always exists. It will be different than the vector and scalar potentials which satisfy the Coulomb gauge, but these two solutions will just differ by what we call a gauge transformation. Now let's see what is the point in choosing this Lorentz gauge. You see, this was our equation for phi. And we had also rewritten the same equation for phi in this form. Mu epsilon del squared by del t squared minus the Laplacian of phi plus del by del t gradient of A plus mu epsilon del phi by del t. This should be equal to rho over epsilon. So this is the equation satisfied by my scalar potential. This is the equations. These two are the equations satisfied by my scalar and vector potentials. You see, these equations are what we call coupled differential equations. The equation for phi depends on A, and the equation for A depends on phi. So we have to solve them together. Well, Coulomb gauge simplifies our life, mainly because it just decouples the phi equation from A. Any dependence on A disappears in the phi equation, so we can solve the phi equation first, and then put that solution in our equation for A, and solve for A. That is the advantage of the Coulomb gauge. Now, in this new gauge, the Lorentz gauge, well, what Lorentz gauge tells me is that it is always possible to find some A and phi that will make this combination 0. So now in this Lorentz gauge, the equations that phi and A satisfy are these ones. The equation for phi and the equation for A, they are decoupled. They are independent of each other. That is one advantage. Second advantage, you see both of these equations are wave equations. So any change that you make by using the driving force, let's say, will propagate only with the speed 1 over square root of mu epsilon, only with the wave speed. So the fact that information is not transferred faster than the speed of light is apparent even at the potential level. That is one of the strengths of this Lorentz gauge over the Coulomb gauge. You see, in Coulomb gauge, it just looks that the phi changes instantaneously when you change the potential, when you change the charge distribution at a given point. But in this equation, if you change rho at a given point, it only propagates as a wave to other points. And the speed of the wave is 1 over mu epsilon. No, you see, what we are saying is that, first of all, you have infinitely many possible pairs, A and phi, that correspond to the same E and the B field. So the question of saying, oh, what is the E and the A and the phi fields, my potentials corresponding to a given E and the B field, doesn't really have a meaning. There are infinitely many of them. Which one do you want? Now, to reduce that possibility to a single choice, we are imposing additional conditions. And one of those conditions that we can choose, if you want, is to set divergence of A is equal to 0. It simplifies your life slightly. At least the phi equation becomes simple. You can just straight away write down the solution from electrostatics. Another possible choice of condition that you are imposing on this A and the phi fields is the Lorentz gauge, gauge condition. So that's another alternative. Or if you like, you can even set other constraints. It's just up to you. Which condition would you like to use? It's your choice. But you should make a choice which would simplify your life. Now, it's not you should, but you better do. Otherwise, your life gets complicated. Why would you like to make your life complicated? Now, these are not the only two possibilities. These are the two most commonly used ones.
Hocam, şu son iki denklemi elde etmek için Coulomb'la Lorentz gauge'leri beraber mi?
No. They are separate conditions.
Yani biri için Coulomb kullandık, diğer için de Lorentz.
Yes. These equations are valid only in the Lorentz gauge. If you impose the Coulomb gauge, these equations will no longer be valid.
The fields are still constant. It's not changing.
No, they are dependent on time.
No, I mean, in Lorentz gauge, electric field was the...
Well, the definition of the E and the B field in terms of my potentials is the same.
In all of the gauge.
I mean, that is basically why we have this gauge symmetry, because those definitions do not change when we make a gauge transformation. Well, the solutions of these equations will also be quite easy. Well, if I would put T over here, that would be just like our electrostatic solution. That is the solution that we have in the Coulomb gauge. Well, this is not T, it is T minus R prime over C. This is what's called the retarded time. This is in Lorentz gauge. This is my potential in Lorentz gauge. Well, what does this mean? Basically, if I want to calculate the potential at the point T, at the position, at the point R at the time T, that will be determined by my charge distribution. But it won't be determined by the charge distribution at the point R prime at the time T, but at an earlier time. Because whatever change I made at the point R prime, it will move at the speed C. And only with the speed C, after some time, it will be influencing my potential at this different point.
Is the factor integral d square r over
D cube R prime. Well, the solution for A is also quite similar. Instead of phi, if you want A, instead of rho over epsilon, just put mu times J. This one, well, okay, let me just write it for this term, and we have run out of time, and we need more time to discuss what this is. So what this basically tells me that, suppose you are moving over here. Or look at the stars. What I see when I look at the stars, let's say there's a star at 4 light years away. When I look at that star, I see its position 4 years ago, not today. So what influences me is its properties 4 years ago, at that point. So this is basically what this factor is. So I'm not looking. What determines the potential at this point, is not what the charge distribution at that point is now. But what determines these potentials at that point, at this time, is what was the charge distribution at that point earlier. How much early? Well, any change will take this much time to travel towards me. Our distance divided by the speed of light. Any change at that point will take this much time to reach my point. So it should be the potential at the time this much before the current time. So this is why we have. Well, this is not a derivation. I'm not claiming that I'm deriving the potential and the vector potential corresponding to these equations, but if you just put these equations into put these expressions into our equations, you will see that they do satisfy our equations. Now we will discuss this in more detail on Monday. Okay, so see you on Monday.